Okay, so today it's implicit differentiation. And implicit differentiation uses the same rules that you've learned about differentiation, except we're going to use them in a slightly different fashion. So if we have some function that we can say y equals, and then some expression, some algebraic expression in x, we do this explicitly. That's what you've been working on. So there's no reason to use implicit differentiation here. But sometimes we get relationships that are not functions. Okay, if I were to take this particular equation, x squared plus y cubed minus 2y equals 3, I defy you to solve for y in there. It just can't be done. All right, so if I were to make a graph, it would look like this. It would look like a little ghost profile. Okay, nice and appropriate for Halloween week. That wasn't deliberate. So even though it's not a function, notice here on the sides it doesn't pass the vertical line test, we can still talk about the slope of the line tangent to this curve at any point. Okay, so I can choose any xy coordinate on this curve, and I can draw what the slope is. And so it would be nice to be able to make a function that tells us what the slope would be with this relation. Okay, so notice, not a function, but we're going to find a function in y that will, or in x and y, that will give us what that slope is. Okay. So this is why we want to learn how to do this, is how do we take the derivative of this without being able to solve for y, but then we need to be able to solve for y prime once we take the derivative. And so we'll be able to get the race of change around that curve for any particular point. All right. So let me use the differentiation operator, d dx. Okay, so if I take the derivative of x squared, that turns out to be 2x, right? You've just taken the derivative. We know how to do that. If I'm going to take the derivative of y, what's the derivative of y? Well, it's just the derivative of y, right? So I can say dy dx. I mean, this doesn't look like an operation, but it really was. This is here I took a differentiation operator and made it into a derivative. Okay, what about this? If I take the derivative of y squared with respect to x. So this is the chain rule, right? So what this is going to be is I'm going to take the derivative of the outer function, which is the squared thing, then I'm going to multiply it by the derivative of the inner function, which is y, which will be dy dx. So this is the chain rule used with just y. We don't really know what y is. I'm just suggesting that if we want to take the derivative of the curve described by y squared, we're going to get 2y dy dx. Okay, now here's a product. Let's say we have x and y and we want to take the derivative of that. So we're going to use the product rule. So then we take the derivative first of the first term, which is dx dx, which we know is what? 1, right? The derivative of x with respect to x is 1 times y, and then we're going to add that to x times the derivative of y. So this really will look better if I put it like this, y plus x dy dx. Okay, so that's the product rule and the chain rule when I'm doing these things implicitly. Now we don't have to write dy dx. We can write y prime, right? So this would be y plus x y prime is the derivative of xy. Okay, everybody up with me notes-wise? Okay, so let me do an example here. What shape is this? Everybody should recognize this. It's a circle, right, with a radius of 5. Okay, so there we have a radius of 5. And we know this point 4, 3 is on the curve, right? 4, 3. So we take 4 squared plus 3 squared is 16 plus 9 is 25. So I want to find the slope of this green line here. So let me use my differentiation operator and say, okay, I'm going to take the derivative of this side and the derivative of the other side. So it's an equation, so I have to do that. So I'm going to distribute this. Notice that I'm taking the derivative of a constant here, which is 0. Now I take the derivative of x squared and the derivative of y squared. And so the derivative of x squared is just plain old 2x, right? There's nothing fancy that I need. The derivative here is 2y dy dx. All right, so that's the derivative. And of course that equals 0. Now I'm going to solve for dy dx because what I want is the derivative. So I have this dy dx thing here. And so I'm going to divide by 2y and then cancel the 2's. And what I get is the derivative equals negative x over y. So if I look at this value, what's the slope here? I know what x is, it's 4. I know what y is, it's 3. And so I have negative 4/3 is my slope. Okay? Everybody follow?
Why is d over dx times y squared dy over dx?
Think of the chain rule. I have a function that's squared. So it's going to be...
I get the 2y part,
Yeah,
but I don't get the dy dx.
Because it's the derivative of the inner function, which is y. Okay?
Over derivative of
It is the derivative of y with respect to x. Okay? All right, so if I look at another line, my blue line here, notice this is what makes it not a function, right? I have a single value of x, 4, and I have two possible values of y, 3 or negative 3. They're both on the curve. So if I want to find the slope here, this is going to be then just, it's just going to be 4/3. And you can see this is a positive slope when it's on this point, x and y, and it's a negative slope when it's on this point, x and y. Okay. So I'll go through a few more examples. Here's that first graph that I drew that looks like the silhouette of a ghost. Okay, I'm going to take the derivative of both sides. The derivative of x squared is just 2x. The derivative of y cubed is going to be 3y squared, right? That's the chain rule, the outer function. Derivative of the inner function y is just dy dx. And so we take the derivative then of negative 2y. So we have negative 2 as a coefficient. The derivative of y is dy dx. And the derivative of 3, a constant, is 0. Okay, so now what I want to do is I want to solve for the derivative. Now, the way this works, when we have these polynomial or these expressions here that involve x and y, we're always going to end up with the dy dx just as a something multiplied by some other expression. So the way we're going to solve for dy dx is we're going to put everything that has a derivative term in it on the left side, everything else on the right side. So in this case, the only thing I have that doesn't have a derivative of y on it is this 2x, so that goes over here. And now I'm going to factor out my derivative of y. And so I get 3y squared minus 2 dy dx equals negative 2. And now I'm going to take this thing that's left over from factoring out the derivative, I'm going to divide both sides, and I get my derivative as negative 2x over 3y squared minus 2. So that means that once I have a point here, if I know what my x and y, if I know a point on the curve, I'll also know the slope of the curve because that's just also an expression in x and y. Okay? Everybody following? Yes?
This is maybe a double question, but why does the d over dx stay with the 3y squared and -2 but not the 2y?
Well, because what I'm doing is, let's take the, we'll use the chain rule blindly, okay? So if we have the derivative of, oops, this should be an x. If we take the derivative of, let's say, y squared, okay, so it's going to be 2y by the chain rule, then the derivative of y we get as dy dx. Okay, so let's do that with x squared, okay? So 2x is the outer function. The inner function is just x. So we have the derivative of x with respect to x. And what does that equal? Just 1. So this is 2x, right? Because whenever you do this, that equals 1. All right? So, I mean, this is using the chain rule really blind because we're taking the derivative of x with respect to x. How much does x change with respect to x? Well, it changes exactly the way x changes because it is x, okay? So that's why dx equals 1. And here, dy dx doesn't equal 1, it equals something else. Okay, so in both cases I'm using the chain rule, but here this simplifies into just 2x. So when I'm taking the derivative with respect to x of just an expression involving x, I just take the simple derivative of it.
So why don't you just do that as a supplement?
Well, because it isn't 2y, it's times, by the chain rule, it's the derivative of y with respect to x. It would just be 2y if I was taking the derivative with respect to y.
Okay.
Okay, it's what I'm taking with respect to. Okay? Okay, so let's talk about some basic strategies in doing this. You can use y prime as dy dx. In fact, you'll probably want to do this because it's a whole lot less writing, right? Y is one stroke, then put a prime. That's a whole lot easier than dy dx. So what you want to do is make rational equations into polynomials. And what I mean by that is when we have something like this, don't get stuck in the quotient rule. Multiply both sides by xy, and so what we get is x plus y equals 4xy. No more quotient rule, it's only product rule and chain rule. All right, so you're going to use product and chain rules. Use them carefully. So I'm going to take the derivative of this now implicitly. Okay, the derivative of x with respect to x is 1, right? The derivative of y with respect to x is just y prime. Now I have 4xy. So I'm going to treat my 4x as one function and my y as the other function in the product rule. So the derivative of 4x is just 4, and then times y, so I get 4y. And then I keep my 4x and take the derivative of y, so I get 4x y prime. Okay, everybody get this? From here to here, this is like crucial. Okay?
What's going on?
You explain that.
Yeah, explain it.
Okay. I'm going to take the derivative of every term individually. What's the derivative of x? It's 1, right? What's the derivative of y? Y prime, right? So I have the product rule, and I'm going to make these two different functions, okay? So product rule is I'm going to take the derivative of this times that plus this times the derivative of that. All right, so the derivative of 4x is 4 times y, because it's the derivative of this times that. And now I'm going to take this, which is 4x. Derivative of y is y prime, right? Okay, so there's where we are. There's the derivative taken implicitly. Okay, now we need to solve for y prime. So what we do with y prime is that we move everything that involves a y prime to one side, everything else to the other. Okay, so I'm going to do that here. I'm going to say y prime minus 4xy. I'm going to move this one over to this side, and I'm going to keep this over here, and I'm going to move my 1 to the other side. Okay, so I've just swapped those two terms, and this is what I have. Everything on the left has a y prime in it. Okay, and so that's what you want to do. And then we're going to factor out the y prime, and then solve for y prime. So what I get is 1 minus 4x times y prime equals this 4y minus 1. And so when I divide both sides by what's remaining after I factor it out the y prime, I get this ratio. So y prime equals 4y minus 1 over 1 minus 4x. And there's my derivative. Okay?
So we use this stuff when we can't use any of the rules.
Yeah.
Well,
If you have a function in x that equals y, so in other words, if your function just involves x, square root of x, x over 3x plus 1, anything that involves an explicit, then you just do your regular derivative of x will equal this, okay? It's when you have something here, you can't solve for y directly here. Okay, I suppose you can. Actually, you can. If you have this, you say y minus 4xy equals negative x, right? And then we'll say 1 minus 4x y equals negative x, and so we have y equals minus x over 1 minus 4x. If I take the derivative of this and then substitute back in y, this is what I'm going to have. Okay? So I could do it in this case. It's a simple enough problem where I could do it either way. But most of the time, like the one with the y cubed plus y, you can't solve for y. Okay. Everybody up with me on the notes? Everybody have a headache? Okay, another example. So I want to find y prime. So the thing I'm going to do here is I'm going to take the derivative of each of the terms individually. So the first term, this xy, I'm going to use the product rule. Derivative of x times y plus x times the derivative of y. So the derivative of x is 1 times y. The derivative of y, or then I'm going to take x times the derivative of y. So I have y plus x, y prime. Okay? Now, I'm going to take the derivative of this y squared. So think about what that would be. What's the derivative of y squared?
2y.
No, not 2y. 2y, y prime. Think chain rule. Derivative of the outer function, which is the squared, makes it 2y. The derivative of y is y prime. So that looks kind of funny when you first see it, but think chain rule, and you got it down pat. Okay? And then the derivative of x squared is just 2x. Okay, so the next step, once we have all our y primes in here, is you want to put all the y primes on one side, everything else on the other. So I'm going to keep these two, move the y over here, and I get 2x minus y. Factor out the y prime. The side stays the same. And then divide by whatever's left over from factoring it out. And so there's my solution. Okay, you all good?
Wait, how'd you get the first part, like the y plus x?
This here is the derivative of that with the product rule. It's derivative of x times y times x times the derivative of y. Derivative of x is 1 times y, x times the derivative of y. And then the y squared is going to be the chain rule. 2y, y prime.
These are all constants, right? Like the derivative of x will always equal 1.
Well, yeah, I mean, that's one of the fundamental rules we have. The derivative of x equals 1. What this is really saying is, how does x change with respect to x? Well, it is x, so they change the same. They're 1.
So you have like a 1 in front of like an x or something. Like a
Yeah.
coefficient like a 2 or a 3.
Mm-hmm.
It's 3x plus 2y.
Yeah.
Like that.
So if we had a coefficient, 3xy,
Yeah.
this would be 3y plus 3xy prime.
Okay.
Okay? Okay, time for you to work. Okay, anybody know what this shape is? What is it? No?
An inverted circle.
How about an inverted? Actually, if you think about different kind of spaces and everything, you could think of this as an inside-out circle, but what it really is a hyperbola. Okay? A hyperbola looks like two parabolas facing each other. Okay, so this particular one would look like this.
I guess that is nice.
Actually, it's the other way. It's like this. Get it?
Are you gonna?
I think you can still see it. Okay, so what we do is we take the derivative of each of these. Derivative of 2x, or x squared is just 2x. Derivative of negative y squared is going to be negative 2y, y prime. Derivative of 4 equals 0. Okay, so then move the 2x to the other side, divide both sides by y, and we get y prime equals x over y. Okay? Everybody get that?
Why?
This is still a mystery, huh?
Yeah.
Yeah. Chain rule. If we have maybe do it like this. If we say the derivative of whatever this function is squared, okay, is going to be this. It's going to be 2 times whatever that function is times the derivative of that function, right? Okay, so if this is y squared, there'll be a y here and a y here. So what this is y prime. So this equals 2y, y prime. Does that help at all?
What would it change if that was dy over dx?
Yeah, it's dy dx. I mean, it's the same thing, right? Taking the derivative of y with respect to x.
That's the same thing as d over dx.
Well, dx y. Okay, this is an operator. We're not multiplying. We're taking the derivative of y with respect to the x. Okay, so that is another way to write that.
Oh, okay.
Okay. Yes.
The derivative of y squared for the section of the chain rule?
Yeah. So you're taking the outer function is the squared, right? So we take 2y. And then we take the derivative of y, which is y prime. And you multiply them. Okay. Here's another one. We'll get a little bit more complicated. All right. Is anybody brave enough to do it on the board? No? All right. So we have the derivative of this times y squared plus x squared plus the derivative of y squared, which is 2y prime, minus the derivative of negative 2x, which is just 2. The derivative of 4 is 0. And then the derivative of negative 4y is going to be negative 4y prime.
It's not just y. Why
Well-
is that y? Wouldn't you just drop it?
Drop what?
No, because for y, whatever the derivative of y is, you have to do y prime.
Is y prime.
Okay, so you can't just drop it.
Well, you can't drop the y because what you're asking yourself here is how does negative 4y change with respect to x? Well, that's negative 4 times the way y responds to x. Yep, all the y primes on this side then. Everything else on that side. Factor out the y prime. And then divide. Where a lot of people get lost is once you have this, they'll get this properly done. But then you have to remember, collect all the y's on one side. Now, if you think about what happens with the chain rule, that whenever we take a function that involves y, the last thing you're going to multiply it by is y prime. So y prime is always going to be just this last thing that tags on any term, really. It's either there or not, so all the ones that are there, you bring over to the left side. Everything else on the right side, factor it out and divide. You're never going to end up with a y prime squared or anything like that. It's always going to be just y prime. So this basic algebra strategy will work every single time. Yes?
Okay, so how did you get the two in front of the x squared y prime?
Because the derivative of x squared is 2x. Okay?
Wait, I think you said that too.
Yeah, like no, I understand that.
This doesn't come from this. This one over there.
Yeah.
This one is this one
You
here.
just moved it
So I
around.
just,
Oh, you moved the 2y in front.
Yeah.
Gotcha. Okay, that's fine.
okay?
I didn't see the 2y.
Yeah.
For the algebra part of it, like,
No.
why can't you like just take out the 2 and divide it with x?
You could. But then, yeah, you could divide it by 2, and so you get 1 minus xy squared over x squared y plus 2. Perfectly good. And actually, that's probably a better thing to do. Oops. Yes.
So the more simplified version would be if you took 2 out?
Yeah, it would be more simplified. And I guess on my... So you could do this at this point here and just say x squared y prime plus 2y prime equals 1 minus xy squared. And then what you're going to end up with is y prime equals 1 minus xy squared over x squared y plus 2. And that's probably a better answer, okay? Okay, everybody follow that? I didn't cancel out my coefficients where I could have.
So is there one more we can try?
Of course. It's always one more. Oh my goodness, a radical sign. Same rules, same process. You can do it. Okay, so let's go after it. You make something that would be very complicated, something simpler, okay, and so you can make it a product of two different functions. And so I'm going to take the derivative of the square root of x times the square root of y, and then I'm going to take the square root of x times the derivative of the square root of y. Notice how this turns out. I do my 1/2 y to the negative 1/2 times y prime. So that's kind of a key thing there. Then take the derivative of 4y squared, and we had negative 8y y prime. And derivative of 12 is 0. Okay, so now what I'm going to do is I'm going to rewrite this thing like this, okay? So you can do it in all fractional exponents if you want. So notice I only have one term that is that doesn't have a y prime, so that's going to go over to the other side. And so here I have this, factor out my y prime. And so I get that. Okay, so what's wrong with this is that it has a compound fraction in it, a complex fraction, I mean, complex ratio. For implicit differentiation, I'll let this one go, although you should be able to simplify this. Actually, let me show you how it simplifies. So what we're going to do is multiply this thing by the lowest common denominator. Which is going to be 2 square root of x, y.